In today's lesson, we are going to address another circle theorem, and it states that a diameter bisects a chord at right angles. Let's address the word bisect. Assuming we have a red line, and this red line is 5 centimeters long, okay, and we can get another line. Let's make that blue, and the blue line touches the red line at midpoint. That is, the blue line divides the red line into two equal parts. Then you have this side to be 2.5 centimeter and this part to be 2.5 centimeter. So in other words, we say the blue line bisects the red line. If what you have is this, if you have a red line and the red line is also 5 centimeter, and the blue line comes on board and divides the red line into an equal part. So let's assume this place is, let's say, 3.5 centimeter, and here is 1.5 centimeter. So we say the blue line intersects the red line. So it doesn't divide the red line into two equal parts. The blue line divides the red line into two equal parts. So the blue line intersects the red line. That's for case 2. But for case 1, we say the blue line bisects the red line. That is, it's dividing the red line into two equal parts. Now, what's our theorem saying? So our theorem is saying that if a diameter bisects a chord, that is, divides a chord into two equal parts, then it does so at right angles. So if it intersects a chord, then it's not at right angle. Okay, so let's have a circle. Let's see what that looks like. This is a circle. Okay, we have a blue circle. Okay, let's make our circle black. All right, let's locate the center of the circle. This is the center, and let's have a diameter. Let's have the diameter of the circle. Okay, so the diameter should divide the circle into two equal parts. Okay, I hope this actually divides the circle into two equal parts. Okay, yes, I guess it does. Okay, I guess it does. All right. Now, that's a diameter. The blue line is a diameter. And let's draw a chord. Okay, let's have a red line to be the chord. Okay, good. Now, if you look at our red line, that is the chord. The blue line is intersecting the red line. It's dividing the red line into two unequal parts. You will agree with me that if we label this side to be x, all right, from this point to this point, we label it as x. And from this point, okay, let's use letters A, B. Okay, let's say line AB is X, and let's say this is C, and let's say line BC is Y. So obviously, X is not equals to Y. So therefore, at the point of intersection, the angle formed, this angle, let's call it theta. Theta is not 90 degrees. Why? Because the diameter, which is the blue line, is actually dividing the chord, which is the red line, into two unequal parts. Let us draw another circle. Okay, let's have this circle here. All right, and let's get a blue line to divide this circle into two equal parts. Okay, and that's going to be a diameter. So let's take our blue line to be a diameter. All right, now let's get a chord. Okay, let's use a red line for our chord. All right, now put our chord up here. Okay, good. Here's our chord. All right, so the red line is our chord. The blue line is our diameter. So obviously the blue line, which is our diameter, is dividing the chord into two equal parts. So we can say this side here is equal to this side. Let's label it A, B, C, D. So we can say line AD is equal to line DC, line DC. So since line AD is equal to line DC, so it means that the diameter bisects the chord. So therefore, that makes this angle 90 degrees. And this one also 90 degrees. Now we're going to use this theorem to solve some problems.
In this example, as indicated, line BD is equals to line DC. Okay, and that's because the diameter AE is the diameter, line AE is the diameter bisect chord BC. Alright, and that makes this angle to be 90 degrees. Yes, angle ADC as indicated in the diagram is 90 degrees. So here is also 90 degrees. Good. You can see that on my reading, that's 90 degrees. And if you look at angle BAC, that's 34 degrees. And the diameter also bisects the angle into, so making this one to be 17. Alright, so angle BAD is 17 degrees. So therefore, we're going to consider triangle BAD now. Triangle BAD. Okay, so what are the angles in that triangle? We have Z, we have 90 degrees, and we have 17 degrees. Okay, everything sums up to 180 degrees. So Z plus 107, okay, 107 is equals to 180. So Z is equals to 180 minus 107. So Z is obviously 73 degrees. In this example, AC is the diameter. Yeah, and that line, the diameter bisects the chord BE. So making line BD to be equal to line DE. Okay, alright, so we should actually consider this place to be 90 degrees. Alright, so that is 90 degrees. Okay, and so we might want to take a look at triangle BDC. So let's label this place as Y. Alright, so if we know our Y, then we can actually get our X. Alright, so if we remember angle in a semicircle is 90 degrees. So angle ABC is 90 degrees. And the reason for that is angle in a semicircle. So angle in a semicircle is 90 degrees because AC is the diameter dividing the what's it called the circle into two. Alright, so that makes 61 plus y. 61 plus y. 61 plus y. The sum of the two is actually angle ABC, and that is equals to 90 degrees. Okay, so y is 90 minus 61. So y is what? 29 degrees. Okay, so since we have our y to be 29 degrees, so we'll consider triangle BDC. Okay, in triangle BDC, so our y is now 29. So y plus x plus 90 degrees, that's equals to 180 degrees. Okay, and our y is what? 29. Okay, plus x, that's 90, 180. So we can say this is 100 and what's it called? 19. That's 29 plus 92. That's 180 degrees, and x is 180 minus 119. So our x is 61 degrees. In this example, we are asked to find the radius of the circle. Okay, let's indicate the center of the circle. Let's take this to the center of the circle. So we are looking for r, which is the radius. Alright, AB is the diameter. Let's label our center to be O. AB is the diameter, and that bisects the chord CD. So making CE to be equal to ED. And if the diameter is bisecting the chord, so it does that at right angles. Okay, alright, so this is 90 degrees. Okay, and we are giving CE to be 2 centimeters. Alright, and we are giving EB to be 1 centimeter. Okay, this is 2 centimeters. Alright, now we have a triangle here already. We have triangle OCE. Triangle OCE is a right angled triangle. So we can use Pythagoras theorem to actually find our R. So let's label this as X, OE. Let's label OE as X. So we can now use Pythagoras theorem, and it states that in a right angled triangle, uh, the square of the hypotenuse side is equal to the sum of the squares of the adjacent side and the opposite sides. Okay, so that makes r squared to be equals to what? S squared plus 2 squared. Okay, so what's our x? Alright, so let's look at the diagram very well. You will agree with me that OB is a radius. Yes, line OB is actually a radius. And OB is what? If you look at OB very well, line OB is equals to x plus 1. Alright, so that means our r, OB is a radius, so our r is x plus 1. So what's our x now? Our x is going to be r minus 1. So that means that wherever we see what's it called, our x, we are going to replace it with what? R minus 1. So let's go back to our original equation. So we are coming from r squared. Recall that we have r squared equals to s squared plus 2 squared, and r squared. So what's our x now? That's r minus 1. Everything squared plus what? Plus 2 squared. R squared. So let's expand this. So this is going to be r squared minus 2r plus 1 plus 2 squared is actually 4. So alright, so let's come up here now. So we're now going to have r squared, let's call it like times plus 2r, 1 plus 4, that's what, 5. Okay, so we have 2r equals to 5, then r is 5 over 2, so our radius is actually 2.5 centimeters.